All right, let's talk about two numbers you see literally all the time, 0 and 1. You probably think you know them inside and out, right? But they have this secret job, a really fundamental role that honestly makes most of mathematics work the way it does. So I gotta ask, what is their real job? I mean, beyond just being placeholders or the number you start counting with. They actually have a formal title and a mission-critical function. Let's dive in and uncover it. So that job title, it's the identity element. And a great way to think about it is like the neutral player on a team. It's the one that can interact with anybody else in the field without actually changing what they're doing. And here's the more, textbook definition. But the key phrase here, the one you really want to lock in, is leaves that element unchanged. No matter what you combine it with, the other thing stays exactly the same. That's its superpower, this kind of powerful nothingness. And here are our two heroes in action. For addition, 0 is the star of the show. Add 0 to anything, you get that same thing right back. For multiplication, 1 steps onto the stage. Multiply anything by 1, and it just stays itself. It's simple, it's elegant, and it is absolutely essential. Okay, now here's where things get a little more precise. As we go deeper, developing our mathematical literacy means we have to be really careful with our words. So we're about to explore this subtle but super critical difference between unity and unit. It's a distinction that really unlocks a whole new level of understanding. Okay, let's really break this down. Unity is easy. It's just the formal, kind of fancy name for the number 1 when it's doing its job as the multiplicative identity. It's one specific thing. A unit, though, that's a different beast. It's any element in a set that has a multiplicative inverse that is also in that same set. So for all the integers, only 1 and -1 work because their inverses are 1 and -1, which are also integers. The number 2, not a unit. Why? Because its inverse is 1/2, and 1/2 is not an integer. See the difference? So why does any of this matter? Well, this isn't just about dusty old definitions. It's a super practical tool. The best way to think about the identity element is like home base in a game of tag. A huge chunk of algebra is really just about finding a clever way to get back to home base. So let's picture this. Imagine we're standing on the number 3 on a giant number line. Our mission, if we choose to accept it, is to take one step and get right back to our home base, the additive identity. And we all know what that is, right? It's 0. So how do we do it? How do we get back home? Simple. We use its exact opposite, its inverse. The inverse of adding 3 is, well, adding -3. We apply that inverse action. And boom, we land right back at 0, our home base. This little journey shows a core principle of, well, everything in algebra. An element combined with its inverse always gets you back to the identity. That's the engine that makes solving equations possible. And here's the proof. When you solve an equation like 5x equals 20, something you've probably done 1,000 times, you're secretly on a hunt for the identity. Your real goal is to turn that 5 into the multiplicative identity, which is 1. And how do you do that? You multiply by its inverse, 1/5. That move isolates x, reveals the solution, and it's all based on that same logic of getting back to home base. A huge part of really getting math, of becoming fluent in it, is learning to spot the number 1 in all of its clever disguises. I mean, think about it. When you multiply by 3/3 to get a common denominator, or the square root of 2 over itself to rationalize a denominator, you're just strategically multiplying by 1 to change how a number looks without changing what it's worth. All right, so far, we've been hanging out in the familiar world of numbers, right? But this whole idea of an identity is so incredibly powerful that it's what allowed math to take this giant leap into the abstract. It's basically the blueprint for abstract algebra, for building entire new mathematical universes that go way beyond just adding and subtracting. In these bigger, more abstract worlds, mathematicians use the symbol E as a kind of universal stand-in for an identity element. And get this, a little bit of trivia for you, that E actually comes from the German word Einheit, which means unity. The rule is exactly the same, but the amazing thing is that the A and the star can apply to things that aren't numbers at all. And this just shows you how flexible this idea really is. I mean, think about a Rubik's Cube. The set of all possible moves you can make, the identity element for that is simply doing nothing, making no move at all, because that's the one action that leaves the cube unchanged. This concept is totally central to huge fields like group theory, which is basically the mathematics of symmetry. It studies these systems where having an identity isn't just a nice feature, it's a mandatory building block. And this isn't just some casual suggestion, it's an axiom. That means it's one of the fundamental, non-negotiable rules of the game. For any system to even be called a group, it absolutely must have one and only one identity element. It is that foundational. So that brings us to this really cool final thought. We've seen that 0 and 1 are just the most common examples, the tip of the iceberg of this much bigger, much more abstract concept. So the question I want to leave you with is this. What other neutral elements, what other home bases, are hiding in plain sight, not just in math, but in the systems you interact with every single day?